Today we're going to talk about how we change the energy of a system. We do this by doing work on the system. Work is a transfer or transformation of energy. Remember that an energy transfer is an exchange of energy between the system and the environment, and a transformation is the changes of energy within a system from one form to another. For work to be done, two things are required: a component of force and a displacement. Work is done when a component of force acts parallel or anti-parallel to a displacement. When that component is parallel, we mean it acts in the same relative direction as the displacement. Anti-parallel means the component acts opposite the displacement. Work is going to equal that force multiplied by the displacement times the cosine of the relative angle between the force and the displacement. Work, just like energy, is measured in joules. We measure the angle relative to the displacement of the object. So here we have a box being displaced to the right. So we'll set 0 degrees as being to the right. Any force that acts between 270 degrees and 90 degrees on the right has a component that's parallel to the displacement, and as a result will do positive work. Any force that acts between 90 and 270 degrees on the left has an anti-parallel component, and as a result does negative work. Any forces that act perpendicular, that is at 90 and 270 degrees, don't have any component that's in the direction of the displacement, and as a result do no work. What about if there are multiple forces acting on the object? The net work is the sum of the work done by each individual force. This can be found by adding the work done by each force or by finding the work done by the net force. We can also find work graphically. The area under a graph of force versus displacement equals the work being done for a constant force or for a varying force. Let's use what we've learned about work to try to answer this question. Which force does the most work? So we have a 10 Newton force that acts perpendicular, an 8 Newton force that acts at 60 degrees relative to the displacement, and a 6 Newton force that acts at 0 degrees relative to the displacement. So the first thing to remember is that a perpendicular force does no work. So our 10 Newton force is not going to do any work. But a parallel component does positive work. So work is done by the 8 Newton force and the 6 Newton force. So that means that A and D cannot be our answers. So now we just have to compare the 8 Newton force and the 6 Newton force. So work is the force times the displacement times the cosine of the angle. In this situation, the only thing that really matters is the force and the angle. For the 8 Newton force is at 60 degrees, so 8 newtons times 60 times cosine of 60, cosine of 60 is 0.5, so we'd have 4 newtons times the displacement. For the 6 Newton force, we'd have 6 newtons times the cosine of 0, cosine of 0 is 1, so we'd have 6 newtons times the displacement. So the 6 Newton force will do more work than the 8 Newton force. Let's look at a couple example problems. A car engine applies a force of 6.5 times 10 to the 4th newtons. How much work is done by the engine as it pushes a car a distance of 75 meters? So in this example, the force and the displacement will be in the same direction, so our angle is going to be 0. So our work will be FD cosine of theta. So 6.5 times 10 to the 4th newtons times 75 meters times a cosine of 0. Cosine of 0 is just 1. So we get 4.9 times 10 to the 6th joules. For question 2, how high can a 40 Newton force move a load when 395 joules of work is done? So again, the 40 Newton force is acting up, the load is being lifted up, so our angle is going to be 0. So work is FD cosine of theta. We need to rearrange this to find the displacement. So displacement will be the work divided by the force times the cosine of the angle. 395 joules divided by 40 newtons. Cosine of 0 is just 1. So our displacement is 9.9 meters. Question 3. A force does 30,000 joules of work along a distance of 9.5 meters. Find the applied force. So again, the force and the displacement are in the same direction, so our angle is 0. Work is FD cosine of theta. We need to rearrange that to solve for the force, which is the work divided by d cosine of theta. So if 30,000 joules divided by 9.5, and again the cosine of 0 is just 1, so 30,000 divided by 9.5 gives about 3,160 newtons. For question 4, a boy pulls a sled at a constant speed of 0.6 meters per second by applying a force of 350 newtons. How much work will be done during 1800 seconds? So again, the force and the displacement are in the same direction, so our angle is going to be 0. Here, before we can solve for the force, or for the work rather, we need to figure out how far the sled moves. So the displacement would just be the speed multiplied by the time. So 0.6 times 1800 seconds gives us 1080 meters. Work is FD cosine of theta. So if 350 times 1080 times the cosine of 0, which is just 1. So the work done is 378,000 joules.